All right, welcome back and to the video lectures on theory of computation, where we're looking at hardness reductions from 3-SAT. This is video 2, where we're looking at reducing 3-SAT to independent set. Okay, we're going to be assuming that 3-SAT is hard, and we're going to be showing that independent set is at least as hard. So if we think 3-SAT is hard, then we think independent set is hard. Great. So let's just go into some details about these problems. So the 3-SAT problem, the input is a Boolean formula f in what's called conjunctive normal form. That means it is an AND of OR clauses. Okay, so there'll be n variables. We'll call them z1 through zn. These variables are either true or false. And we're going to take m OR clauses and AND them together. So each clause Cj is ANDed together. Okay, and each clause Cj has 3 literals, and we'll denote those Lj1, Lj2, and Lj3, and those, it's an OR clause, so this clause is the OR of those 3 literals. Okay, each literal is a variable or its negation. So a literal is like zi if it's a variable, or it's zi bar if it's the negated variable zi. Okay, and of course, if zi is true, then zi bar is false, and vice versa. Okay, so we're looking for assignments to variables that will make this formula true. Okay, and if this is an AND of some OR clauses, well, then what does it need to be true? Well, at least one of the literals in each clause must be true. Okay, why? Well, if one of a OR clause literals is true, that means the clause is true, and if the AND of a bunch of OR clauses, we want that to be true, it better be all of them are true. Okay, and so this is a decision problem, and the answer is yes, if there exists an assignment to the variables of true and false that makes it true. Great. So what is the independent set problem? The independent set input is a graph on vertices V and edges E. Again, an edge goes between pairs of vertices, and target theta independent set size. Okay, the output to independent set is a decision problem. The output is yes, if this graph has a subset of vertices that is both independent and large. And independent means for every pair of vertices in that set, there are no edges between them. The idea is edges correspond to conflicts, and you can't take 2 pairs of vertices in your set that are conflicted. Okay, we also want this set to be large. In other words, the size of this set has to be at least theta. Cool. So let's talk about what goes into a 3-SAT reduction. So reducing from 3-SAT to some other problem, y. Okay, again, we're trying to show that y is as hard as 3-SAT by reducing 3-SAT to y. Okay. So 2 key points of what we're trying to do here. We're reducing from 3-SAT to y, which means we're trying to solve 3-SAT. We have a funny computer that knows how to solve y, and we're trying to solve 3-SAT. Okay, and so whenever you do a 3-SAT reduction, we're always trying to solve 3-SAT. Okay, and this is sort of interesting. It's opposite of how things usually work with computers. Usually you have the same computer and you try to solve new problems with it. Here we have the same problem every time. It's 3-SAT, and we're trying to solve it with a different computer, a computer that has a magic black box that solves a different problem, y. Great. And how are we going to use this computer to solve y? Well, we have to use the constraints of y to ensure the constraints of 3-SAT. Great. And what are those constraints of 3-SAT? Those constraints are the following. So in order for 3-SAT to be true, we need a representative literal in every clause to be true. Okay? And these representative literals in every clause have to be consistent, meaning two literals in different clauses can't both be the representative true literal if they correspond to the same variable, but one is taken positively and one is taken negatively. Okay, so these literals cannot be corresponding to the same variable and its negation to be both representative true literals. So they have to be consistent. Great. So that is what we're doing. And again, our problem today for this video component is to reduce from 3-SAT to independent set. Showing independent set is at least as hard as 3-SAT. And again, independent set is trying to find a subset of vertices that is independent and large. Great. Let's jump in. So just to make sure that we don't forget our key points, I've written them down here on my notes. So we're trying to solve 3-SAT with a black box for y, and we're going to use the constraints of y to ensure that the constraints of 3-SAT are satisfied. All right, let's dive in with our 3-part reduction. The first part is the forward instance construction. Okay, and so what does a forward instance construction do? So I'm trying to take my 3-SAT instance and map it to an independent set instance so I can run this magic computer with an independent set solver, get my answer yes or no, and I'm going to just say that's the answer to 3-SAT. Okay, so I am trying to map a 3-SAT instance F to an independent set instance V, E, and theta. And I'm going to write little f's on these to say that they are coming from my 3-SAT instance F. Okay, cool. And I wrote an example down here because it's sort of helpful to walk through an example first before we start actually doing anything. Okay, so we want to use the constraints of independent set to ensure the constraints of 3-SAT. And so what are my constraints of 3-SAT? So my constraints of 3-SAT are that each clause has one representative true literal, and representative true literals are consistent. Okay, so look, here's my idea. I'm going to create a vertex in my graph for every literal. Okay, so let's just draw those. Okay, so here we have L11, L12, L13, L21, L22, L23, L31, L32, and L33. These are vertices corresponding to the literals in my clauses. I have 3 literals per clause, so I have, and these are my M equals 3 clauses. Okay, so the first thing I do is I want to have one representative true literal per clause. So I'm going to make sure that only one of these vertices corresponding to literals in the same clause gets selected. How do I do that? Well, in independent set, I know I can't select multiple vertices if they have edges between them. So I'm just going to put edges between all the vertices in the same clause, like this. Okay, and Cool. And I want to make sure to make sure that we can solve 3-SAT, I want to make sure that I have one representative vertex for each of these clauses. Okay, and so I'm going to require my independent set size be at least m. So I'm going to set theta equal to m. And so already we know if this is going to be a yes instance of independent set, it better be I have exactly one vertex selected in each corresponding to each of the clauses. All right. And what's my other constraint here? 3-SAT, representative true literals are consistent. So I need to make sure that I don't select two literals that correspond to that conflict. Okay, so let's look at our graph and just find two such literals. So um, here we go. So we have uh, we'll say Z2 here and Z2 bar here. Okay, so Z2 in the first clause, and Z2 bar in the last clause. Okay, so these literals conflict. One is the variable Z2, one is the negated Z2. We can't have both of them being true. And so I want to represent that we can't select both of them in our independent set. Okay, so what I'm going to do is put an edge between them to represent that we can't select both of them in our independent set. And now any independent set can't have this edge between them. Cool. And I'm just going to do that for all the literals that conflict. And so let's see, we have Z1 here in the first clause and Z1 in the last clause. So I'm going to put an edge between Z1. Let me just make some more room for myself. Z11 and L11 and L31. Great. And look, I've got Z1 in the first clause, Z2 in the first clause, in L12, and I've got Z2 bar in the second clause, L21. And so I'm just going to draw an edge between those. Great. Now I have the Z2s pretty figured out. Okay, and I have my Z1s pretty figured out. What about Z3? So Z3 is in clause 1 and L13, and it's in clause 2 as L22. Okay, and Z3 is not in either clauses, so that's good. And what about Z4? Z4 bar is the third clause in the last two. So we have this. Now, I think we got them all. But if we didn't, you could go in there and figure out the rest of them. Great. And so what have we? So this is actually looking pretty good, right? Because now we're guaranteeing our two constraints are satisfied. Each clause has one representative, sort of got that, and representative true literals are consistent. They can't conflict because we put edges between the ones that conflicted. Okay, and so we're going to collect an independent set that's large, its size at least m, which here is 3, then we have to have one of them per clause, and we have to have them not conflicting, and so we have to have a solution to 3-SAT. Great, so let's write down our construction. So step 1, let's have a vertex for every literal. Okay, so LJK is going to go to and give me a VJK. 2, I'm going to introduce clause edges. Between vertices that correspond to literals in the same clause. Okay, so these are going to look like VJ1, VJ2, VJ2, VJ3, and VJ1, VJ3. Okay, so I'm going to add these for all J. Okay, and 3, I'm going to add conflict edges. Okay, between vertices that correspond to literals that conflict. Okay, that is, I'm going to add the j k, the j prime k prime, if there exists an I such that the ljk equals zi and l j prime k prime equals zi bar. Okay, so these are going to be my clause edges. These are my conflict edges, and so we'll call this E prime and E double prime, and I'm going to set E f is equal to the union of E prime and E double prime. Okay, and then finally, as I said before, we're going to set theta equal to m, the number of clauses. Great. That is our part 1 forward instance construction. And now we need to do parts 2 and 3, which are going to be the certificate instructions, and they're going to correspond to our if and only if proof that f is a yes instance if and only if this independent set instance we've constructed from f is a yes instance. Cool. Before we do our other specific instructions, let's just make sure that we analyze our runtime. Okay, and what is the runtime of this algorithm? We can make sure it's polynomial time. But look, in fact, this is a linear time algorithm because we are just processing yeah, so part 1, a vertex for every literal, that's order order m because there are 3m literals. Part 2, a clause edge, that's order m because there are 3m clause edges. And the conflict edges between vertices, that's going to be for every vertex, it occurs in one of the literals, so I have to check this edge for each literal, and so that's going to be, well, if I was bad at it, it might be something like m squared. Okay, so the total here is, if I was, lazy about this, it'd be order m squared. Probably thinking smarter about it, you can do it in order m, but it's not important. We just need it to be polynomial time. All right. Okay, part 2 is our backward certificate instruction. Okay, and what are we doing with the backward certificate instruction? We're imagining we've got a certificate for independent set, and we're trying to show that uh, we're trying to find a certificate for for 3 set. Okay, so we have an S uh, independent set, and we're trying to construct a certificate for 3 set. Okay, and how we're going to do this. Okay, okay, for each variable zi, what we're going to do is, if there exists vertex in SF labeled by zi. So if there's a vertex in F that corresponds to a literal that's labeled by zi not negated, okay, then we're going to set zi to true. Okay, so if there exists such a literal, we'll set it to true. Okay, else we're going to set it to false. Okay, so we're just going to loop through all the variables, see if they're true somewhere, correspond to true literals in, see if the variable corresponds to a literal that is not negated, and if it does, we're going to set the variable to true, otherwise set it to false. Great. All right, and now we need to prove that this algorithm always succeeds. Okay, so I'm going to start off with a claim. Okay, my claim is that if a vertex is labeled by z bar, then no vertices are labeled by z. Uh, okay, so if a vertex in S is labeled, corresponds to a literal that's labeled by zi bar, then no vertex in S corresponds to literals labeled by zi. Okay, and why is this? Well, S is an independent set, and by our construction, we have edges between every zi bar and all the vertices corresponding to literals corresponding to zi. Okay, so because of those edges, if we've selected this vertex into S, it means we can't have selected the vertices corresponding to any of the other literals into S. Okay, so this is because there are conflict edges. Okay, because they're conflict edges and because we have an independent set. And so we can't select both of them. Okay. Now I'm ready for the main claim that this part 2 backward shift construction is correct. Okay, so I claim that if S is independent and the size of S is at least M, then the formula on this assignment I've just constructed is true. Okay. Let's prove this. S first of all, the independent set must have size exactly M. Since it has size at least M and it's independent, we know it has size exactly M. Why is that? Well, because we have the clause edges in the independent set, that means we can select at most one per clause. So if we have size bigger than N, M independent, it has to be size exactly M. It's independent. Okay, so SF has size exactly M. And that means we have exactly one vertex per clause. Okay, and now we're just going to check that, again, we want to show that this formula is true on this assignment. So let's just check for each clause that each clause is true. Okay, so for each clause J, and VJK, which is in S. Okay, remember, so S has one vertex per clause, so let's let VJK be that vertex in S. So there are two cases. If LJK is ZI for some I, it's not negated. Okay, well then let's go back to our, let's look at our construction. Our construction says for each ZI, if there exists a vertex in S that's labeled by positively, we set zi to true. Okay, so here is a vertex in F that's labeled positively, so it must have been we set that to true. Okay, and now what about the other case? If LJK is Zi bar. Okay, and now we get to use our claim. Well, so if a vertex in S is labeled by Zi bar, then no vertex in S is labeled by Zi. Okay, so we know that no vertex in S is labeled by Zi. Okay, and so by our construction, there does not exist a vertex in S that's labeled by Zi, so we don't set it to true. We do the else clause and we set so we set Zi to false. Okay, and great. And so notice that in the case that the literal is not negated, we set the variable to true. And in the case the literal is negated, we set the variable to false. And so in both cases, the literal is true. Okay, and this was just any literal, any clause j, and this holds for all j. And so every clause j is true. And the formula is satisfiable. Great. And now we have part 3. The forward certificate construction. Okay, and what are we doing with the forward certificate construction? We are mapping a Z that is satisfiable, that satisfies F to a independent set that's large. Okay, so how are we going to do this? Let's let S prime correspond to vertices in the graph that correspond to true literals. Okay, so let's let S prime be the vertices Vij such that the literal, sorry, let me get my indices correct. Vjk corresponding to Ljk that is true under the assignment of assignment Z. Okay, But this S prime might not be an independent set because some clauses might have more than one true literal. So what we're going to do in our next step is uh, if any of the clauses which are correspond to triangles in our independent set have more than one true literal, we'll drop all but one of them. Okay, and this is going to give us what we'll call our selected independent set. Great, so that's our construction, and now I claim that if f of z is true, then s of f is independent, and size of s of f is at least theta equal to m. Okay, great. All right, well, all clauses have it. Let's start by just the assumption that f of z is true. So this means that all clauses have a true literal. Okay, so s prime is at least m. Okay, but now if we throw away extra true literals in each clause, we get down to having one vertex corresponding to each clause, and so we get the size of SF is exactly equal to m when we throw away all but one in each clause. Great. So that's showing that this is theta. That's showing that the one condition of independent set is satisfied, that the size of the set is large enough. Okay, now we have to show that it's indeed an independent set. So we have to say that for all we'll say v j k v j prime k prime in SF. We need to say that they are independent. We want them to, so two things have to happen. One, vjk and vj prime k prime not in the same triangle. Well, that's true because we dropped all but one. Good, so they don't violate the clause edges. And now we have to check the conflict edges. Okay. And so we know that LJK and LJ prime K prime both true. Okay, so in fact, if they're both true, they must not conflict. And so it must be that there's no VJK, VJ prime, K prime edge, because these are not conflicting literals. So combining these two observations, it must be that SF is independent. because no pairs of vertices selected in SF have edges between them. Great. And so that is our claim. Okay, let's just recap a little bit of what we did. So going back to some of our key points. We solved 3-SAT with a black box for another problem y. That problem y in our case was independent set. We used the constraints of y to ensure the constraints of 3-SAT. What were those constraints of 3-SAT? Each clause has one representative true literal, and representative true literals are consistent. Great. So that concludes the second video lecture, reducing 3-SAT to independent set. If we believe that independent set 3-SAT is hard, then now we believe that independent set is hard. In the next lecture, we will reduce from 3-SAT to Hamiltonian cycle. Talk to you soon.